Welcome. Today we are discussing Module 2.1, the RAG Paradigm Shift and Architecture Theory. Here is a quick look at where we are in our curriculum. Welcome back to our AI channel. Today, we're diving into Module 2.1, the RAG Paradigm Shift and its Architecture. RAG, or Retrieval Augmented Generation, isn't just another acronym. It's a transformative approach that's redefining how we interact with large language models. It fundamentally shifts how LLMs access and use information, moving them beyond their static training data to become dynamic, knowledge-seeking entities. This empowers them to provide more accurate and relevant responses. The main drivers behind RAG's emergence are two critical limitations of traditional LLMs: hallucinations and stale knowledge. LLMs, brilliant as they are only as good as their training data. This means they can't access information published after their knowledge cutoff date, and they sometimes confidently fabricate answers when they don't know something. RAG acts as an external memory and fact-checker, giving the LLM current, verified information to work with, thereby making their outputs far more reliable. Let's look at the foundational architecture of RAG. It operates in two major stages. First, we have the indexing phase, where all your external data, documents, databases, web content, is transformed. This data is chunked into smaller, manageable pieces, and then each chunk is converted into a numerical representation called an embedding using an embedding model. These embeddings are then stored in a specialized database, often a vector store, which is optimized for similarity searches. This entire process prepares your knowledge base for rapid retrieval. The second stage, the retrieval generation phase, happens in real time when a user asks a question. In the retrieval generation phase, when a user inputs a query, that query is first converted into an embedding using the same embedding model used during indexing. This query embedding is then used to perform a similarity search within the vector database. The goal here is to find document chunks whose embeddings are closest to the query's embedding, indicating high semantic relevance. These top K most relevant chunks are then extracted and prepared to be sent to the LLM. Finally, with the user's original query and the newly retrieved context in hand, the generation component takes over. These are combined into a single, comprehensive prompt and sent to the LLM. The LLM then acts as an intelligent summarizer and synthesizer, using the provided context to formulate a factually grounded and coherent response. It's a powerful combination that enhances the LLM's capabilities dramatically. Understanding this theoretical framework is essential before we move to practical implementation. In our very next lecture, Module 2.2, we'll get hands-on and start building a Hello World LLM chain with LangChain, practical.